Alright, here we are back at part 3, and we have an example of a metal called sodium, and its work function is 2.28 eVolts, and that is the amount of energy it takes to hold its electrons. Any greater than that, then the electrons will fly out. Let's say blue light is hitting the sodium metal, and we are going to find the maximum kinetic energy of the electrons that fly off. Alright, so I'll show you how to do this, and you'll do some similar ones. You're going to pick up the equation that Einstein gave us, the relationship E equals H times, K times F. Then we called it H. It was a constant, so I think that was right. E equals H times F. And we learned that Planck's constant was 4.14 times 10 to the minus 15. And the frequency, well, we said it was blue light, and I think if we look back on our handout, the front page of our handout, blue light, blue light, blue light. Can we tell what blue light is? I think it is hard to tell from that, so we have to be given the fact that blue light has a frequency. You know what? We're going to go and figure out the blue light. Alright, because here's the blue light. It has, actually, we're going to use 4.25, so the blue light we're using is right in the middle of the blue spectrum here. So right here, and I'll give it to you. It's 425 nanometers. So back to the drawing board here. So blue light has a wavelength that we know, but we don't need wavelength, we need frequency. So if we know that the wavelength of blue light is, say it is given to us as 4.25 times 10 to the minus 7 meters. Alright, so we won't work in nanometers, we'll go right to the tiny meters. And I want to find out what this value, frequency, is. So if we have to grab the other dance we like to dance between equations. So we know that frequency equals velocity over lambda. So the frequency is what we need, so we're going to have to calculate it. Velocity, since it's light, 3.0 times 10 to the 8th. And lambda is 4.25 times 10 to the minus 7. So we have to stop there and get the frequency before you can go back here and calculate the energy. So the frequency, after we do that, we we divide these two numbers, we get 7.1 times 10 to the 14th. It's frequency, since we kept it in meters and meters per second, we end up with hertz. So coming back up here, we have E equals 4.14 times 10, forgot the 10 in the top part here, 10 to the minus 15, where your two hands up, times the frequency, 7.1 times 10 to the 14th. So when I multiply those two together, I get 2.9 eVolts. So eVolts, 2.9 is a unit for energy, and we are going to recognize that that is not the complete answer, because the problem indicated that the sodium metal had a work function of 2.28 eVolts, yet the energy that this blue light gave to the sodium metal was 2.9. what do you think I'm going to do with the work function of 2.28? And again, the question was find the max kinetic energy of the electrons that fly off. So what we know is this has to be overcome before any electron will fly off. So we're going to take the energy that the light brings and we're going to subtract from it the 2.28 eVolts. When I subtract 2.9 minus 2.28, I get 0.6 eVolts. So that is the energy, the most energy that any electron flying off could have. If all the energy from the light transferred to the electrons, then we know that the max they would have is 0.6 eVolts. All right. These are the kind of concepts, and this formula, dancing around with this formula, those are the ones that you're going to need in order to do your OYOs. So the OYOs will be 11.7, 11.8, 11.9, and 11.10. All right. The back of your mod will show you the answers. If you get stuck, they do a really good job, if you read it all through, of explaining every step on these. So please complete these 4 in class, and no homework. It's the weekend, and we'll pick this up on Monday if you don't finish, but hopefully you will. All right, that's it for this Friday edition. It's a lot to take in, and you did it. So carry on, class. Carry on.